Development Program on strategic approaches and emerging trends in data science. Today, we are honored to have with us a distinguished expert in the field of artificial intelligence and computer systems, Dr. Satyajit Das. Dr. Satyajit Das is an assistant professor in the Department of Data Science and Computer Science Engineering at IIT Palakkad. He holds a joint PhD program, PhD, from the University of South Brittany, France and the University of Bologna in Italy. And his research spans across cutting-edge areas such as systems for AI, architecture, methods, and tools for low-power systems, including coarse-grained reconfigurable architecture, custom processors, multi-core systems, high-level synthesis, and compiler optimization. Currently, Dr. Das leads the Multi-Coreware Academia Global Innovation Center for Artificial Intelligence at IIT Palakkad, where he is actively involved in pioneering research and innovation. His extensive expertise in AI-driven systems and energy-efficient computing makes him the perfect guide for today's session. Dr. Das, we are truly privileged to have you with us today. On behalf of all gathered here, on behalf of FISAT Engineering College, we welcome you, sir, to this session. Thank you, sir. Over to you.
Thank you. Thank you, Dr. Prasad, for the introduction. I'm really happy to be part of this program. And so I'll be presenting today on the deep learning framework. I hope you have a very good introduction in the previous days regarding the deep learning and its applications, deployments. So today we'll be mostly going towards the deployment portion because it is indeed necessary in this modern era of deep learning and the boom of AI. We will see a large range of deployed deep learning models in every devices at our daily lives. So essentially, if we see the deep learning breakthrough, there are several frameworks that have been coming. However, in the deep learning models that you have seen so far, mostly the two stages that are important for the deployment, and that is for the training phase and the inference phase. So in the training phase, you are seeing here that we have a set of data that is actually for the deep learning. We need a large amount of data for training phase. And this large amount of data are fed through the model. So these models are basically deep learning based models. Now, in today's age of deep learning, we see models in terms of vision application models. There are models regarding the language models. There are models regarding the neural networks, graph-based models, and so on. So all these different types of models are actually coming under the same umbrella of deep learning. And the pipelines that you are seeing here for training and inference are completely are essentially similar for all these different types of models that you see today. So this large amount of data are fed through these models, and the output is essentially called the forward network or feed forward pass. So through that pass, we get the output from the models, and the output of the model is essentially benchmarked or compared to the ground truth, and then the backward pass happens based on the loss that has been computed at the output. And this backward phase or the backward pass essentially computes the gradient of the loss function with respect to different parameters that are being used inside these models. And this essentially goes through several iterations and epochs till we get optimized loss or basically minimized loss, which we are computing at the output. So if we understand the entire pipeline, then it will be easier for us to see how it is implemented using the different frameworks. And today we'll be using the PyTorch framework for the deep learning models for the training and inference, especially. In the inference phase, we are interested only to get the output, essentially for detection, prediction, or any other regression tasks, or let's say generative tasks. So for this, we use the inference phase just to pass the input through the model as a feed forward pass and get the output at the end. So this is essentially the two phases of deep learning life cycle that are essential to deploy in different devices. And in modern era, we see the devices from the edge till the cloud, and the entire spectrum of computing devices actually deploy these different types of models based on their computing capacity. So few of these aspects that we will cover today to see how we can optimize the models for deployments and so on. So to begin with, we have this TENS framework, right? So we are talking about frameworks. So essentially, frameworks are nothing but to a quick development environment that are facilitating this deployment very easily. So we need to write the entire codes or programs for all the micro steps for the deployments for both testing and training, or inference and training. These frameworks help us to automatically compute few of the stages like gradient computation and so on. So we do not need to go deeper into the computation and deployment or implementation of these micro steps. And these frameworks also help us to efficiently deploy the models for both the CPUs and GPUs. So today I'll mostly talk about the CPUs and GPUs because we will not go into other devices like TPUs and FPGAs and other accelerators like NPUs. So those are also devices that are used for deploying these deep learning models. But mostly we use GPUs and CPUs for running the models. And for these kind of devices, these frameworks should have the wrapper from, let's say, cuDNN, cuBLAS, OpenCL, so on, so that we do not need to go into the micro management of these operations based on these libraries and optimizations. So these frameworks essentially help us to build or go through deployment very quickly with the help of different wrappers and functions and modules. Why PyTorch? Because there are several other frameworks also available. We'll probably see a few of them, but PyTorch is mostly used in research and development purpose equally, because it helps us to both go into few essentials of the models for research purposes, as well as it has few wrappers or let's say few APIs which help us rapid deployment for the development phase. So it's open source, obviously, and it's developed as at the Meta's research lab, AI research lab. Earlier it was known as Facebook's AI research lab. And it leverages the power of GPUs and modern NVIDIA GPUs as mostly because all the different optimizations are mostly built on the cuDNN libraries. And it helps us automatic computation of gradients, and it makes us easy to test and develop the new ideas for the models. So that's why it's also easier to use it in research purposes also. As I was mentioning, there are several other frameworks like CNTK from Microsoft, Caffe, several versions of Caffes are there, Keras, TensorFlow, Theano, and other frameworks like MXNet. Today we will focus on PyTorch, and we'll see the usage of PyTorch to develop these models for both CPUs and GPUs. So before going into the details of the models, how it works and how the deployment works, the tensors are the most important data structure in the PyTorch library. or PyTorch framework. It is similar to NumPy arrays. If you have used NumPy arrays, it's exactly similar. However, it can be used also in GPUs for faster computation. Similarly, if you see this example, uh, this is the module import for the PyTorch module import, and this torch module can uh, initiate or initialize different tensors. So here we have initialized two-dimensional tensors with random values as x, and another y tensor actually initializes this 3 by 3 uh, tensor here. And to print the tensors, we can use print x, y, print y. So as I was mentioning, that it's the data that we are being more interested to work with in the deep learning models. So we can uh, initiate or initialize these data as zeros, because most of the times uh, we need to have this flexibility to initiate large tensors of several million of dimensions as zeros at several many models, and we can also initialize these tensors with values. So if we have values, we can put values also, and torch tensor will automatically can infer their dimensions. So we can use size functions to print the sizes and the dimensions of the tensors. We can add tensors. We can have several operations that we can perform. So here we have two-dimensional matrix as x and y, 4 by 4 matrix of size 4 by 4, and here these are initialized as tensors, torch tensors, as you can see, with random values, and these can be added with this add function. We can print, and all these indexing of these tensors are similar to the NumPy array, so there is no change in the tensor indexing as such. So in the model development, at several times we need to resize and reshape the tensors, because this is very important from the point of view of let's say new model development or model transformation or model augmentation. So this resize and reshape tensor functionality or flexibility will help you to go through very easy reshaping of these tensors. Here is an example. As you can see, x is initialized with the random tensor 4 by 4 tensor here, and y is kind of reshaped from this x tensor in one dimension, and you can see the 16 elements for this x tensor has been uh, 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 reshaped to this y tensor as an one-dimensional array here. And similarly, this is another z tensor, which is reshaped from the x dot view. So view function is for the reshaping, and you can see -1, 8 will reshape it in a two-dimensional, but the number of elements in the two dimensions will be different, because in the second dimension now we have 8 elements, and in the first dimension with the -1 indexing we have the automatic generation of the number of elements, which is basically 2. So this -1 will help you to automatically estimate the index value or the number of elements in that particular dimension. Because it is essential, because for the larger dimensional of tensors, when you will use very huge tensors, it will be easy to derive the number of elements in that particular index or particular dimension to estimate. So the print of x size and y size will give you the exact tensor size. As you can see, for z we have 2 by 8 of dimension, which is reshaped from the x tensor here. Okay. So torch.rand n we can initiate one tensor here. You can see here 1 by 4 by 32 by 24. So one matrix, you can think it of 32 by 24 matrix with 4 such matrices and one such set of 4 such matrices. So this way you can initialize any dimension of tensor as such. And with this view of 8 by 2 by minus 1 by 3 by 8, it will automatically derive which will be the number of elements in this dimension, which is basically 8 in this case. So torch tensor versus NumPy array, because as I mentioned that these are basically same data structure. However, the flexibility for torch tensors are you can use it in for CPUs and GPUs both, and for the NumPy arrays it can be used only for CPUs. So here is an example of NumPy arrays and conversion from NumPy array to the NumPy data structure to the torch. So torch dot from NumPy can transform the NumPy arrays or NumPy data to the torch tensor. So this is also very widely used function, because many of the data set that we import as NumPy arrays, and we can import it to the torch library tensor, and then we can use it for our deep learning models, which will be running in the GPUs. So if we transform it to the torch tensor, it will be easier for our deep learning. Matrix multiplication is, I think, the most widely used function for the tensors. And here is the function that can be used for the matrix multiplication. Here mat1 and mat2 are two randomly generated 2 by 3 and 3 by 3 matrices respectively. And resultant matrix is res, and torch.mn, which is the matrix multiplication function that we are calling by sending these two matrices as arguments. The resultant size, of course, while we are doing such operations, the dimensions should be compatible, because 2 by 3 and 3 by 3 will generate resultant matrix as 2 by 3. If the dimensions are not compatible, then we will have errors. Similarly, we can do batch matrix multiplication because 10 such batches of 3 by 4 matrices that is been initialized here, and similarly 10 such batches of 4 by 5 matrices are initialized in batch 2. And you can see that resultant matrix is the batch matrix multiplication between the batch 1 and batch 2. So the resultant matrix size will automatically be 10 by 3 by 5. So similarly, these are the flexibilities that we are seeing to use such module with different operations, which can estimate its sizes. Based on the sizes, the resultant tensor sizes will automatically be defined, and we do not need to go through any additional transformations and reshaping. In addition to the matrix multiplication and batch matrix multiplication, we have many other functions or operations that we can apply on the tensors. And you can check the documentation in this link. You can just copy paste this link, and you can see how many such operations and functions that we can apply on the tensors. Basically, concatenation, the squeezing, unsqueezing, these are also changing the or reshaping the torches. And tensor concatenation is widely used for several language models as well as recurrent neural networks and so on. Okay? So these are widely used functions that we use for the tensors. So once we talk about tensors, now these tensors are basically the inputs and outputs of the deep learning models. And here is one computational graph of deep learning model which are used to compute y from x, w, and b. This is basically nothing but multiplication and addition of these tensors. So x and w are the are generating a by multiplication and addition to the bias, which is generating the y. Considering all these data sets as tensors, it is easy to derive the computational computational graph. So any model in PyTorch first gets converted to the computational graph, and we need to visualize the computational graph to essentially uh, deploy or write the model code. Obviously, if you let's say download any model from the already existing repository, you will not be able to visualize as such. But if you see the computational graph of these models, you can see exactly how many layers are there, what are the inputs and outputs of each layer, and how the input is passed through different layers of networks and tensor transformations to generate the output. Here is this simple example, and we'll try to see how this implementation goes. So AX is one tensor of 2 by 2 dimension that is being initialized as ones. Once we can initialize with ones, zeros, or random values, and any other initialization functions that we can use for initialization. So this is another very important technique to optimize the code of your model development in PyTorch by knowing the different initialization functions that are available for tensors. Here, two such tensors are initialized, x and y, and we are doing this W initialization. Now, in this initialization, we are seeing that x, y are initialized with ones with 2 by 2 dimension and 2 by 1 dimension, whereas the W vector or W tensor is initialized with 2 by 1 dimension, but requires grad equal to true. That flag is set. That means in our training, which are the parameters which needs to be updated through the training process or along the training process, those parameters need to be initialized as requires grad equal to true. However, if you are using different versions of PyTorch, the initialization of these different parameters can be different. So you need to exactly know which version that you are using, and based on that you can use different flags. Or like in other frameworks, you do not need to maybe initialize the requires grad equal to true, which is explicit here, but many other frameworks uses implicit flag as grad equal to true, which means these parameters are needed to be updated in the training process. Similarly, biases also need to be updated, which are the tensor here. And this computational graph uh, has this implementation of or initialization of these all these vectors as such. So here we are let's say doing one prediction, which is computing this linear combination of W, X, and B as matrix multiplied of a matrix multiplication of X and W is added to B, and that is passed through a sigmoid activation, and this P is generated. And in the output, we are computing this loss function, which is explicit here. Here we are doing a cross entropy loss function computation based on the ground truth, where P is the output prediction, and the loss function is computed based on the output prediction, and the Y is actual prediction. So this is how the loss function is computed for the cross entropy loss. There are many other losses, and for loss function we might not need to use explicit let's say declarations, and we can use many implicit functions that are already used in the loss function repository. And then the cost function is calculated based on the loss computed over all the data set or the tensors that are being, the data points that are being applied, and the average is being computed, and that's how the cost is being computed here. Any deep learning model has this inherent objective to minimize the cost, and that is being done using the gradient computation. And here we are doing the gradient computation by using this backward function. And backward is the only function that you can use for this. We do not need to write even a module or any function implementation to do the backward pass of the model train. So cos dot backward will automatically compute the gradient of the loss function with respect to all the parameters at different layers automatically. And we can print the gradient of the loss function with respect to W, with respect to V, and then we can use the gradient of the loss function for our training of the neural network or any other deep learning model as such. So for our training procedure, we have several stages. Like first, we need to define the neural network of the model, and then we have to iterate over the data set for the inputs. And this is actually the two stages of the model deployment, which can define the performance of the model. Because how the data set is being read and how the data set is being read throughout or across the CPU, GPU, all the different computing devices that you have. We'll talk about modern approach to use these iteration over the data sets, how we can use the data to accelerate the model training for modern frameworks like PyTorch towards the end. We have the next third step as the processing the input through the network, and then the loss computation, because this loss will be the gradient of the loss will be propagated through the all the layers by using this back propagation. So propagate gradients is the fifth stage, and the last stage is essentially updating the weights of the network. And throughout the training process, by updating weights, we'll minimize the loss function or loss value in the end, which will give us the performance or accuracy or the better predictability of the model. So first, how to define our neural network? Very simple example that we'll go through to understand how we can use it as a function. So nn.modules are usually used. Nn is the package, and module is the class that we will inherit to write any model, which will actually override this forward method, and we can write this forward function to write the forward pass for the model. And then the backward pass will take this NN or the model, and it will need the loss function to be computed. But for backward, we do not need to write a function, as I have mentioned before. So here is an example of a network class, which is the implementation of a very simple feed-forward network. As you can see, the class net is the inherited class from the module class, nn.module, and here is the constructor initialization, which will create the different layers or initialize the different layers of this deep learning model. And then the forward function will define the feed forward function, how the layers are connected and how the different layers are taking the input tensor and generating the output tensor. And we do not need to generate or write any backward function. So these are the definition of the network class. So here is one very simple MNIST CNN from MNIST dataset, which takes 32 by 32 data as input, and it passes through several convolution and pooling layer, and at the final 3 stages we have a few fully connected layers, and this is the model that we'll see how to implement, and then we'll move forward to the advanced models. So here is the class net definition. As I was mentioning, it's inheriting the nn.module class, and the constructor here will initialize the different layers. So this is the initialization of the first 2 convolution layers. So 2D convolutions are used as the first 2 layers, and the dimensions of the tensors are you are seeing. Yes. The the dimension of the tensor that you are using here, 1 by 6 by 5. One is the batch size, 1 by 6. One is essentially uh, uh, the batch size. The 6 is the output channel, so input channel, output channel, and then the kernel size or the filter size for the convolution operation. So any function that we use to, let's say, define one layer, we will have several arguments to give, and that will basically based on, will be defining the layer dimensions. So these are the input and output dimension for the convolution layer, and first convolution layer and second convolution layer, as you can see. So 6 output uh, channels are given as input to the 6 input channels here, and 16 output channel of the convolution 2D of the second convolution, and 5 by 5 kernels are used for this convolution. And then the 3 fully connected layers are defined as such with the different dimensions. And then the last fully connected layer has the output layer of, or output dimension of 10, which defines the 10 classes of the MS dataset. So this is just the constructed initialization with the all the layers definition. And then the forward pass will actually define how these layers are connected to each other. As you are seeing here, this convolution layer 1 is connected to this ReLU activation, and then the output of the ReLU activation is connected to the max pull 2D, which is the max pull or the downsampling operation that are being performed in the first layer. Similarly, this second max pull 2D and then the flattening of the output of the max pull 2D is initialized here, and then the computation of 3 or connection between the 3 fully connected layer has been done, which is through the fully connected layer 1, fully connected layer 2, and then output of the fully connected layers are passed through ReLU activation function. So this is how the entire forward pass is formed. And as you are seeing here, the definition of these tensors or dimensions are basically based on the definition that we have initialized in the constructor. Now the better practice of this type of deployment or development is to use similar tensors. So as you can see here, we are using X as the input as well as the output for each of these connections. So input X, output X, input X, output X, input X, output X, and so on and so forth. So this way, we will not be messing up with any tensor as such, because all the tensors are using same name of the X. To define a bigger model, if we use different names or different variable names or tensor names, then it gets confusion. So usually this is the standard practice, and that way we can easily debug also in the debugging phase, because this is just the computational graph that we are making to facilitate the computation. We can have the helper functions also, like here we are using this num flat feature helper function to help the output of max pull 2D to get flattened, which is basically one function that is flattening function. This is just for demonstration purposes. There are inbuilt function for flattening as well. So all these inbuilt functions are helping us to define the model parameters and initialize the model. So this is the 3 functions that we have initialized, and then we have defined the input image, and the output of the image is passed through several convolution and fully connected layers. Now this forward function will actually take us through the connections as I have just discussed, and then the helper functions will help us to execute some of the functions that we are trying to customizedly build for this model training or inference as such. So the next stage is to iterate through or iterate over the data set of the inputs, and data we can get data set from several sources. Like for image data set, we can go to Pillow, OpenCV, and there are many other data sets that are available. I mean sources. Uh, for audio, SciPy, Librosa. For text, NLTK. So these are different packages that are that are used for different data sets or open data sets that are available. We need to load the data into memory as NumPy array, and then we can convert to tensor for the GPU. So because when we access these data sets, these are mostly converted as NumPy array, and then they are used for CPUs to extract and store into the memory, and then from the memory we can transfer it to the GPU using the different transformations. So here we are using this torch vision to, let's say, export or import some data for vision purposes or vision tasks, or running for any vision related algorithms. So here this torch vision dot transforms module will be imported. So these transforms module will be used to transform our data, or let's say if we are applying any normalization or any other transformation to the data, we can do it easily. So here this normalization is applied to this data set for this mean standard deviation of 0.5. So this is how transformation, there are many other transformations available that we can use. And then the segregation of train set and the test sets are done. So here we are using the CFA10 dataset for downloading the data. So here we are using different flags to set that this is the set that we are training, and this is the set we are downloading also, and the transformation is also applied. So as you can see, with this very simple API of transform, we can directly transform any data set and download it for the train set. And then data loader is essentially uses this or basically this is a inbuilt sampler which samples the data from the downloaded data and sends it to the different workers for the training or testing. So here we are seeing that we are creating a train loader data set for the data set here, and this data loader is essentially working for the train set which with a batch size of 4. So as at one time it will fetch 4 such the data with shuffle true, that means randomly shuffle the images, and then take the data and it will send it to the number of workers, 2 workers, let's say. So this is the 2 number of workers that are being deployed for this data loader. So we can actually optimize the performance based on the different number of workers. We can vary, and we can vary the batch sizes as well for facilitating different types of training, and the speed of the training we can control from here as well. The next is the test set. So for the test also, we are downloading the data for the test, and we are keeping this data at this, let's say, path with train equal to false flag, because these data set are not being used. So the data loader not be applying this training data set, or would not be drawing any data from the test set as such. Similar transform is used. So we are creating another test loader here for the testing of the data set. So after the data set loading, then we need to process the network. So this is also very simple because we have already defined the forward function, and the computation of loss function is also very crucial because that also defines the network performance. So here is one such definition of MSC loss, or mean squared error loss, which is defined as NN. So NN will have different packages of loss function, as I mentioned. So here we are using MSC loss. So output of the network and the target is basically the initialization of, let's say, 10 such random variables for the output 10 labels that we are creating. And then we are essentially reshaping the target tensor here. And then the criterion is setting the loss as MAC loss. And then the criterion is, or loss is being computed based on the output of the network and the target, which is the randomly generated target or the values that we have created. So here we are computing the loss between the output of the network and the level. Now this target can be ground truth also, or any other target that are interested of or interest to us for the comparison and loss function computation. The second last stage is the backward pass. So backward pass essentially computes the gradient of the loss function based on the different, or with respect to different parameters at different layers. So backward function calling will actually do this either it's gradient descent or stochastic gradient descent based on the criterion definition. It will automatically do. And the last stage is the upgradation of the weights of the network. And to update the network, we can use, as I was saying, that optimizer. Any optimizer that you can use. There are a plethora of optimizers that are available in this Optim package. SGD is the stochastic gradient descent. There is ADAM optimizer, the ADDM. So there are many such optimizers that can be used with different parameters. And then the optimizers dot zero grad, this function will initialize all the gradients at 0. This is essentially at the beginning of the training stage, and the output of the training network is computed, and then the loss function is computed based on the output of the network and the target. Target is basically the ground truth here, and then the loss function is computed using the using this gradient, using the backward pass, and optimizer dot step will update the parameters with the optimizer that we have initialized here. So this is essentially the crux of the training stage. So just to give one example, so the let's say we have 8,000 or 80,000 training samples. We have batch size of 50. That means each iteration will take this batch size, and it will iterate through all the images. So each epoch will actually go through the entire training set with a batch size of 50. So basically, if our training takes around 30 seconds, so how much training time we can have for 3 epochs that we can estimate. So this kind of computation actually help us to essentially analyze and a priori see exactly how much time we are going to invest for the training. And based on that, we can actually optimize the different stages of the training phase for faster training, or let's say optimized training. So here is a full training phase where we have defined the model as inherited net, and then the train loader is defined, criterion is defined, the optimizer is also defined. And for each epoch, so here we have 2 epochs. For each epoch, we are going through the train loader with batch size of whatever batch size that we have defined. For I, it will iterate through these batches, and then the another batch will be selected for the epoch. So each epoch will actually traverse through all the data elements of the training data set, and then the loss function will be computed, and then the updation of the parameters will happen. And this is how the training phase will basically work. So then the zero grad or any other, if any other optimizer is defined, that is fine. And here is the track of this is just one way of tracking the loss after every 2000 batches, because each time if we see the loss or the accuracy, it might not be relevant because after maybe 2000 batch, we'll get some meaningful output in loss or reduction in loss. So here is one such way to keep track of different, let's say, loss values in our training phase. So this is very basic of training pipeline that we have just seen. And in the end, after the training is finished, we can actually save the model, which is basically the updated parameters and other different, let's say, layer dimensions or uh, definitions of the layers connections. Everything will be saved in the path that we are setting here. So torch.save will save the model in that particular path, which can be used for later inference or testing phase. So this is another example of testing, so which actually loads the model from the path in the in this function, and then the output is computed based on the different images from test set. So here we have this test loader, and then test loader is loading the test images here and passing it through the downloaded model, and then it's generating this output here. And in the end, we are unpacking the output as the predicted value and the probability value, which is maybe not relevant to us. That's why underscore is used in this fast packing dimension. And predicted value is basically the output of this neural network. So this is a very simple pipeline for testing, which is basically the forward pass of the entire model. To train the model on the GPU, we need to first define our device. If we have CUDA cores, it will automatically detect this CUDA is available function. And if it is available, then a device will be set to the CUDA core. If you have multiple GPUs, that will be set as a list. And either of the GPU that we can use at the list index. If it does not find the CUDA core, then it will set the CPU as the device automatically, and then we can transfer the model to the device as net.to device. Also, to transfer the data and the labels, we can also use for the data .to function to transfer the data from the CPU memory or unified memory to the GPU memory. And then GPU can actually start the training process for the training. So the training can be also done to the multiple GPUs. We will see how to do this training in multiple GPUs. But before going into that, I'll just go through a very simple a few simple things that I just wanted to show you so that you have some reference. So if you go to the pytorch.org, you will have all the related resources for any deployment or development or research purpose that you want to use. If you go to the ecosystem and developer resources, here you will have all the resources. And the resources means any types of documentations, discussions, tutorials, GitHub links for open source already developed codes and the complete pipeline. A few examples if you want to search for in different applications like Vision, Text, RL, and different other applications. There are maintainers and so on. If you want to go into the entire details of the PyTorch, you can download this book also. So this is an interactive deep learning book, which is a very good book as per my suggestion, which you can look into that. And also, if you are more interested in training, you can actually go for PyTorch training. This is training means this is just a few training tutorials that you can go through. Now, in the tutorials, you will be able to see different blocks of tutorials. So, so for different models, like let's say audio-based models, NLP, different applications, age deployments, different quantizations, let's say optimizations. If you want to use, you can use that. So how to go? You can just go. Let's say I want to search for quantization. You can go to the quantization, and you can see how you can do the model quantization for different deployments. So similarly, let's say if I want to see the dynamic quantization of an LSTM word language model, if I just go to that model or go to that tutorial, we'll be able to see the entire notebook that we are actually interested in. So here I'll just go through each stage to show you how to actually read this type of tutorials. So these are basically the packages which are needed to import, like NN, as I was mentioning. NN all the functional APIs are here. We are importing as F. Torch, of course. This is the PyTorch mother package. So here is the LSTM model, or long short-term memory based model, which are defined here, which is basically nothing but a recurrent neural network based model. And you can see, as I was mentioning, all the model definitions are kind of same. Here is your constructor definition, where we are initializing all the layers, as I showed you the example. Here is the helper function to initiate or initialize the weights, and the forward function will define the forward pass of the function, how the layers are connected, and this is another helper function to initialize the hidden layers. So this is just the model definition, and this model definition can be used for our model training. For this particular case, the data is being used as text data. Here, this is a class which is dictionary class that is being developed for making the dictionary from this corpus class, which is basically taking the different tokens and adding it to the dictionary to make the entire data set. So this is where we are actually downloading the pre-trained model, which is nothing but a pre-trained model which is already trained, and we are downloading it. And for the evaluation, we can call this evaluation method, and it can actually print the model as let's say how many dropout layers are there, which are the dimension of the LSTM layers, what is the dimension of the hidden linear layers, and so on. So so this is basically nothing but the helper function for the model download, and this is exactly where we are actually doing the or opening the model and initializing the inputs, initializing the hidden layers, and then the generated data that you are seeing here. Okay. So now this is a very basic model, basic LSTM model that has this evaluation. Now we can use this torch.quantization.quantize dynamic for dynamic quantization. So dynamic quantization is nothing but one example of optimizing the model for performance. So quantization is reducing the weights or converting the weights to lesser number of bits. Let's say here the weights are converted to integer 8 values. So that means 8 bit of integer values. And this is how the model quantization works. So we are importing this quantization torch.quantization, and then the quantized model is basically nothing but quantized dynamic with the model and the model parameters, and we are printing the model because we have quantized. So the dimensions of the data that are required, that has been quantized with qint, as you are seeing here. So that means our model is now quantized, and then if we use that model for our let's say if we just save that model or see the size of the model, we will see the reduced size of the model. So here the mother model had around 113 MB of size, and the reduced size for the quantized model is now around 80 MB. And when we run the model for our evaluation, so the original model was taking around 200 seconds to process the input data, and here we have reduced, let's say, elapsed time without any loss in the accuracy here. Okay, so it's almost similar loss. So this type of quantization we can apply. So this is just one example where we can go and see exactly how we can use these different let's say tutorials into our advantage. So here is an example of, let's say, real-time inference on Raspberry Pi of one image video model by using quantization. So similarly, there are many such practices that we can follow, like for NLP, for parallel distributed training. So that also I'll discuss briefly in this session. So one important part of any training or let's say the deployment is profiling the models. So if you see the more profiling of PyTorch, there are several profiling of applications and trace analysis and different approaches are there. So you can go to different profilers to see. Here today I'll just show you how to use this Torch Vision profiler. Torch Vision, sorry, the TensorFlow or this T profiler. So here is one model I have, which is basically inside this device. As I mentioned, this model is basically called for training with all these different parameters and criterions and optimizers that are initiated here. And this model has convolution 2D block, then different sequential blocks, and then we have the output dimension of 1000 classes. So this is the training method for training the model, and here we have the profiler. So this is the Torch profiler. We are initializing the profiler as prof. So now this profiler can be used without context or with context. So I'll provide this notebook also for your reference. Essentially, what is the expected outcome of the profiler is basically the different usage of the devices. As you are seeing here, how much GPU is being used, where is exactly the bottleneck that is happening, how much memory copy happened, and which are the kernels that has been done, how many kernels was done, and the different usage of different, let's say, portions of our model. Okay. So from this analysis of, so this is basic ResNet 18 model, and with this we can actually profile the running of the model on the device as well as different performance metrics of the model as well. Okay, we can actually do a diff between different runs that is not run here, but that also we can do. With the profiling, we can also profile the execution summary as well as the different kernels that are being used, which are the how many calls happen to those kernels. Let's say this convolution kernel from cuDNN library that has been called 60 times. So if that profiling is actually not matching to our model definition, which is let's say taking up a lot of duration or a lot of cycles here, then we can go back and revise our model and come back to see whether we have optimized the this calling of this library or not. So this kind of analysis helps us to, let's say, efficient deployment and development of this type of frameworks very easily. So this is the tensor board profiler. As I have mentioned, there are other profilers also. PyTorch can be used, these profilers directly and indirectly. So we'll come back to the scaling of the training, because once we have the train pipeline set up for the models, then we would like to scale up the training for, let's say, larger data sets, larger batch sizes, and larger dimensions of the model parameters. So there are two approaches to do the scale up or scaling up, which is data parallel and model parallel. Data parallel is nothing but data distributed, because sometimes what we need is to process data parallelly and bring the data to one model and process it and then get the output. This data parallel helps us to process the data in parallel and actually increase the data input throughput for the models. The model parallel, on the other hand, actually model distributed way. So here what we do usually is distribute or replicate the model across different GPUs for let's say partial running of model at different GPUs, and then aggregate the model output at different stages. So these are the two approaches based on the requirements of the model as well as the requirement of the deployment. We can use either. So for data parallel, we have this single machine data parallel and distributed data parallel. And for model parallel, we have single machine model parallel and distributed model parallel. And mixing these two, we have distributed data parallel with model parallel. These are nothing but just some notions of how we want to segregate or, let's say, create different instances of either the model or the data that we are using for the training. So here is an example of single machine data parallel. As you are seeing that we have the output of the model, which is gathered at the GPU 0, which is basically the main orchestrator, if you can think of, which is essentially scattering the data to different instances of different other GPUs and gathering the data after processing. Let's say this M is replicated across which is the let's say different data processing modules, and which are replicated here, here, and here, so different GPUs. And then we are running or getting the output of this processing here from or gathering the output, and then we are computing the loss at the same machine, or which is the host machine here, or host GPU here. So this approach is essentially to help the data processing in parallel across the different GPUs. However, one machine is running the model and actually updating the data, the parameters based on the loss function. And this is one such example of data parallel. So if we want to do data parallel, we can actually send the model to the CUDA 0 and do the data parallel model using nn.data parallel method, and it will actually compute or do the processing of the data parallelly across the different GPUs that we have. Similarly, if we have single machine model parallel, that means we have the optimizer that is being replicated in two different GPUs, and then the optimizers are actually running sequentially based on this output of the first GPU 0 is fed to the second one. So this is a sequential way of doing. However, we can do the pipeline manner of execution, and it can actually accelerate the function. So here we are not actually doing the backward pass in the other machine. So we lost computation on backward pass, and the upgradation is happening in GPU1 only. So here is an example. So here essentially this model is or model or net, which is initialized at GPU0, GPU1, subdivided to subnet 1, subnet 2, and these two parts are executed in GPU0, GPU1, and then the aggregated functions are actually collected. So essentially we are setting the model at CUDA 0 and CUDA 1, which are the two GPU instances here we have. And then the training loop is as such or similar to whatever we have seen so far. In the distributed data parallel or DDP, which this is actually the most interesting one, and in the modern age of large language models, mostly these distributed data parallel approaches are adopted mostly. So if we have multiple GPUs like GPU0, GPU1, GPU2, GPU3, and we can have in different machines altogether, they can sit in different parts of the network as well. We do not mind, because actually the models, the entire model are replicated into all these GPUs that we have. So essentially the optimizer, the loss function, everything is being computed at each GPU as you are seeing here. GPU0 is computing the optimizer as well as the loss function, optimizer loss function. GPU2 also, GPU3 also. So all these have the model instances, and then the data also is parallelized uh, across the different GPUs. And this is also actually done by one backend. Basically, there are data communication backend. So CUDA or NVIDIA has its own data communication backend, or Nickel NCCL, which is widely used. Also, PyTorch has its own data communication, let's say, module, which actually creates these groups of GPU instances and then rank them. And based on the rank, it actually assigns different tasks and actually replicates the model across these different GPUs. So as you are seeing, I0, I1, I2, I3 are applied to all the instances at all the GPUs here, and then the loss function is computed. But there is this all reduce function, which is actually running as a circle here, because at each stage of this forward pass of the model through the network, all the upgrades or all the let's say details of the optimizers are actually passed or shared, and the aggregation happens at each machine, because all will have the updated optimized value, and they are aggregated, and then the each parameter is optimized at the for backward pass of each machine instance. So this is one sample code snippet for running the distributed data parallel. So DDP is the API that we can use. Torch.distributed.init process group will initiate the process group with the backend. Basically, the backend can be initialized with any backend communication protocol. As I was mentioning, mostly it is nowadays Nickel or NCCL is used as backend. However, based on the world size, rank, and the backend, this distributed initiate process group will be defined, and then the different GPUs will be initiated, and the model will be transferred to different GPUs or replicated by nn.parallel.ddp. So this DDP API will actually create instances of the same model across these devices of this group that we have created here. And then the training loop will do the training. Basically, this spawn method actually creates one one multiprocessing spawning. So it will create one process per GPU to instantiate the modules, the models, and then it will actually create the training pipeline based on the training pipeline that we have initiated. So this is the usual way of modern day uh, uh, model training for deep learning applications and models. In the pytorch.org uh, repository, here you can see we have parallel and distributed training. And here, distributed data parallel, there are video tutorials also. If you are interested, you can go deeper into the DDP implementation. And DDP implementation will be very, very important when we go forward with different large language models and transformer-based models and so on. So this, along with the tutorials, you will have the resources, all the notebooks. You can get it from here, along with the data sets and comparisons. So this repository has the definition of or whatever tutorial that we have seen, all the implementations are here, and the implementations are also given as let's say the entire pipeline setup, so you don't need to go elsewhere to find out the missing pieces. So with this, I'll go to one more important aspect of PyTorch, uh, which is actually PyTorch Lightning. So if you have heard about PyTorch Lightning, it's actually a very good tool to do the uh, rapid deployment. So in modern days, we need to develop the models very quickly. We need to test it, and we need to set up for debug also. And actually, it's a large pipeline that we need to set up for different models, because some models will have also backend models as such. Because let's say if you have uh, transformer models which are tasked for vision transformer, same transformer modules you can use by changing the backend of the model for your NLP tasks and so on. So for this kind of rapid deployment, PyTorch Lightning is very good. PyTorch Lightning is nothing but a very lightweight wrapper which helps you to scale the deep learning code structured for different uh, applications. So, so what it does is that it helps to create uh, automatic checkpoints. Distributed training makes precision training, because if we have one model to train with mixed precision, you need to actually change different sets or different places at the training pipeline. But with this wrapper of PyTorch Lightning, it's very easy. Just you can actually define what kind of how many types of precision you want to use at different stages, and that will be used for your training the multi-precision stages. It also integrates seamlessly with the PyTorch. That's why you can actually use it at very high level, at model level, as well as different, let's say, stages of debugging of the models. And so this Lightning actually has some of the use cases. So you can actually go into this repository, and inside the torch you will have the necessary things for your Lightning model inputs, so that you can actually look into that. So this is where we will actually conclude, and this is another. Okay, so this is the main pytorch.org that we are using for all the references. So yes, with that we will conclude, and if we have any questions, I'll be happy to discuss now, and I'll share the codes, the basically the profiling code, and as well as the different references that I have used after this session. If you have questions, we can discuss. We have 10 more minutes for our discussion. Can use my. So I was talking about this book. You can download this book, the PDF version, the PyTorch version that you can use. Basically, this PyTorch version will take you to the different, let's say, aspects of the several models basically at one place. So you have convolutional neural networks, you have attention-based models like transformers, and you have natural language processing models, pre-training, training, different applications like vision applications are also implemented, natural language processing applications. Also, their generative adversarial networks or GANs are also implemented. So all the different implementations of different models, as I had mentioned, you can actually go through this. It has all the necessary prerequisites, a brief description of the models, and then the necessary code for the models and expected output. So it's a go-to one-go book that you can refer for complete deployment of different deep learning models. Okay, so thank you. If you have any questions, we can still discuss. I'll start sharing now. I
Thank you,
think
sir. I think participants can interact.
so the book I just showed you, which book you can actually refer. So you can, yeah.
Okay, I think there is no further interaction.
Okay.
I invite Assistant Professor Nitya for vote of thanks session. Nitya, Nitya miss.
Okay, sir. Good evening, everyone. It's my privilege to extend a vote of thanks as we conclude today's first session of 6-day faculty development program on strategic approaches and emerging trends in data science. First and foremost, our sincere gratitude to our esteemed resource person, Dr. Satyajit, for delivering such an insightful and engaging session on deep learning with PyTorch. It was a truly enriching experience, and we have learned so much from your expertise and in depth knowledge. On behalf of Federal Institute of Science and Technology, Angamali, I extend my heartfelt appreciation to our esteemed resource person, Dr. Satyajit sir. Thank you so much, sir. I also take this opportunity to express my gratitude to all the participants who have actively engaged questions and made these sessions made more interactive and fruitful. Once again, thank you, Dr. Sir, Dr. Sajid sir, and all participants. Thank you and have a nice evening.
Thank you.
Now it is break time. We can have a 5 minute break. We can start next session at 7:30. Thank you.
Good evening, Anand.
ഞാനാ
Good evening, Anand.
Hi, good evening, Irene.
Anand, do you want to check your presentation?
Yeah, let me try. Is it looks good? Screen?
Yes, Anand.
Okay.
Shami ma'am, are you ready?
Yes, sir.
And sir, shall we start? I am Prasad. Shall we start, sir? We will introduce you first, then we will start. Okay.
Okay, sure. Yeah.
Okay. Shami ma'am, please.
Am I audible?
Yes, miss.
Good evening to one and all. I welcome all of the delegates for today's second session of Faculty Development Program on Strategic Approaches and Emerging Trends in Data Science. Today, we have with us an eminent resource person, Mr. Anand George, Principal, Technical Engineer, Oracle America Incorporated, USA, to handle a session on AI vector search in Oracle database. Mr. Anand brings over 17 years of experience in the software industry with a strong background in software development and Oracle database administration. For the past 10 years, he has been working with Oracle Corporation in USA, leveraging his deep expertise in database technologies. He holds multiple prestigious certifications, including Oracle Certified Professional and Oracle Certified Architect across various database versions. Additionally, Anand has expanded his expertise into cloud technologies and AI, earning a certification in Oracle Cloud Infrastructure Artificial Intelligence. With his extensive experience and certifications, Anand continues to drive innovation and excellence in database and cloud technologies. With immense pleasure, I welcome Mr. Anand George to handle the session. Welcome you, sir.
Thank you. Thank you for the introduction. And thank you for the opportunity to be a resource person for this session. And I thank all the FISAT organizers and especially Dr. Irene Babu for introducing and organizing this session. So with that, I will start my presentation. This is AI vector search in Oracle database. So basically, in past few sessions, you were going through the various technologies and how the those technologies are developed and all. So now in this session, probably you can expect how the enterprise world is using these technologies. So more than technical, this will be you can think about the session like how the enterprise world is accommodating these emerging technologies in their products and all. Okay, with that, I'll go into next slide. I'll have a funny trivia question. If you would like to respond to that, you can do it in the chat. So this is a question that what is the deep blue? So if you are aware about the deep blue, you can respond that in the chat. Yeah, so I can see a couple of answers. Okay, so this is a just playing supercomputer that was introduced by IBM, and this is famous for defeating the world-class chess champion Gary Kasparov in 1997. So this is considered as a historic moment in the artificial intelligence and computing, as it marked the first time a world champion lost a match to computer under standard tournament conditions. So I included this slide just to give an idea that artificial intelligence is not really a new thing. If you trace back, AI is a half-century old discipline where machines were trained to think and act like humans. Even though it was not as popular as now, it was still there. Okay, but those times there were a difference, like the the way the AI is being used. So that was more like a algorithmic AI, where it's asked to carry out the task and make some predictions. So if you look at the way it's worked, it recognized a pattern in a set of data and uses that, and it uses what it learned to make the predictions on the new data. But now we have the generative AI where it creates something new. It can be audio, text, or image. Any new data, it can be generated. So how does it doing it? It's like recognizing the complex multidimensional patterns based on a massive data set, and then it generates something new that is similar to the training data set. Okay, so this is just for an introduction. Now, going back to the agenda, so I have these items to discuss. So first we will see about the Oracle, a quick overview of Oracle, and then what we will look into what is vector search, and followed by that we will look into why Oracle is now adding the AI vector search into their database product. And then we will look more deep into the AI vector search and the generative AI, and we look how the AI vector search is being implemented in the Oracle database, and we'll end with the key takeaways. Okay, so to start with the Oracle, a quick overview. So Oracle is a multinational technology company known for its database, software, and cloud solutions. The key offerings of Oracle is Oracle Database, that is a powerful relational database management system, and Oracle Cloud, that is cloud computing services, including SaaS, PaaS, and IaaS. And Oracle also provides enterprise applications like ERP, CRM, and HCM solutions, etc. So just to give an idea about Oracle again, like some of the numbers, you can see that how much contribution it's providing to the world. So it's been there for 47 years, and most of the Fortune Global 100 companies using Oracle database for their applications. Oracle has 79 OCI regions, that is cloud regions. So it is implemented across the world where they are providing cloud services. So this slide represents the volume of Oracle databases being used around the world. Out of 194% of the Fortune Global 100 companies are using Oracle database. If you take the top banks, 14 of the top 15 banks in the Fortune Global 500 list use the Oracle database as their database for their services. Okay, so this gives some history about Oracle, how it started, how it's releasing its versions, what are the major releases that is starting from 1977. As you can see this slide, Oracle started as like Oracle soft. It's like a software development laboratories, that is the SDL, and later it's changed its name to Oracle. And over this period, they have released the multiple versions of Oracle database. You can see like each of version included multiple features. When the internet is introduced, Oracle started giving the product through the internet. Then when the grid computing came in, it's become the grid using Oracle 10G or so. And later, when the cloud is emerged from 12C Oracle database version onwards, Oracle is using cloud technologies. Now, in the latest version of 23 AI, Oracle is providing many features that is useful for the AI. So the latest version of Oracle is Oracle Database 23 AI. It's a next generation converged database where you can handle all the database needs of a software or of an enterprise application. So this is the latest release of Oracle's flagship database. It is released due to more than 300 new features plus thousands of enhancements. So during each of these releases, Oracle will add major features and many enhancements. This is one of the major release over the last few years. So this comes with AI vector search, which is a new feature added to the Oracle database. So this is a slide just to show you like some of the major features that is being added to the Oracle 23 AI. Out of this one, we will be focusing on today AI vector search. Okay, so now like normally the databases have traditionally performed value-based searches. That is, like if you give a particular value, you will get the result from the database. So if you want to find a product, you will give the name in the where clause, and you will get the result. Or if you want to get the product using its name and price, you can give that specific value. It will return the exact results. But now there is a growing volume of unstructured business data that must be searched by semantics or meaning that you cannot give the exact search criteria when you are doing a search. So instead of that, sometimes you need to give the description of the product what you are looking for. If you are searching for a product, you may be giving it the description, or you will be giving it even a photo of that product, and you wanted to match that products that can be that are similar to that product. So in such cases, you cannot use the traditional RDBMS database or its SQL capabilities. So for that, um, vector search is the breakthrough capability for searching the data by semantics. So instead of doing the value search, vector search is doing it searching through the data by using the semantics. Again, what is a vector search? So a vector search is a new technology that enhances the information retrieval by mapping queries to relevant data in your database based on semantics instead of precise matches, using the vector generated by AI or ML embedding models to measure the similarity. So basically, it looks for the similarity using the semantics. Now, vectors are used in AI to capture the semantics of the data. If you have multiple type of data like images, documents, videos, or even structured data, you still can use the vector and it will capture the semantics of the data. So how does it doing this one? So vector is you can think of a sequence of numbers that is called dimensions used to capture the important features of the data. So it represents the semantic content of the data. It's not storing the actual words in the document or pixels. It's normally produced by any embedding models. So, so the main operation that vector can do is like mathematical distance between them. So if you have two vectors, when implemented, it is looking for the mathematical distance between these two vectors. So there are different mathematical distance formulas like Euclidean, cosine, or Fermi, etc. So that can use and find out the mathematical distance. So here is an example how this vector is being created. You can look at the example like if a house image, if you have a house image, the house will have different features. So each of these features, it is represented in a number that is constructing this vector. So if you look for the type of the roof, decorations, number of stories, the material that is used for the building, all these can be considered as features of that house. So this information that will be mapped as a number and will be represented in the form of vector. So this is just an example, just the example for our easy understanding. But if you take the actual algorithms, it will be using more complex features and there will be lot of dimensions. So once you have these vectors, it's easy to handle these vectors. So basically how these vectors are being treated in the applications, right? So when if you have two vectors, it's actually trying to place these vectors according to its similarity. So if in this case, right, if you look at these two images at the top, if they are similar, they will be placed close, and if they are not similar, then this vector will be far away from the other two. So you can think like if the similar entities are coming, they will have a shorter distance between their vectors. This is the key feature of the vector that is being used in the AI vector search. So even for the word similarity, it is working the same way, where word vectors that are close are more semantically similar. So if you take the example here, all the fruits, they are coming together when you place them in the vector. And animals, if you have different animals that will be coming together. So the documents and the image also works the same way, and the document vector that represent the similar content are closer than those represent the similar content. So how the Oracle database is using these vectors, right? So what Oracle database has done is it has created a new vector data type that is being used to insert the data. So we will see more about the vector data and all, but this is the basic of the usage of the vector. So it is using a vector data type. And how we use that in the application. So if you want to find the house that is similar to a picture, you can use a vector function that is called vector distance. So if you have the vectors stored, that is the features of the houses, you can input another picture, and that will be converted to a vector, and that vector will be used to fetch all the similar images that is we giving us the input. So the interesting thing is this has been made simple. If you know how to use a SQL query, you can easily incorporate this vector search into your queries. So there is no really machine learning expertise required, even though you are dealing with an AI technology, AI feature. So any DBAs and developers, they can use this AI vector search without having a machine learning expertise itself. Now, it's even adds more flexibility because it allows the queries that combine the AI vector search with business data about the customers and product. So the SQL queries that you might be knowing that it can have the where conditions, and it can have the joins, etc. So if you want to know, in this case, right, it's an example, if you want to know the houses that are similar to the picture and it matches some of these criteria like customers preferred city and budget, etc., you still can use that filtering conditions along with the vector itself. So this makes the customer data is being combined when you are doing the AI search, and it is like it's an integrated solution that is easy. So because it doesn't need to add anything extra, capabilities are already there. That is, you can have the combination of the RDBMS database features plus the AI feature. Now, in order to understand, like from an enterprise perspective, why Oracle is adding the AI vector search? Because Oracle is known for its Oracle database and its cloud technologies. But why now Oracle is adding this feature into the product itself? Okay, so Oracle's goal is like to enhance the enterprise business application by integrating semantic search, unlocking the powerful new use cases. So basically, when the world is moving towards the AI, all the enterprise business data that is resides in the databases that that also needs to be exposed to this AI world. So in order to do that, if you can run this AI features inside where your data is already residing, that will make the applications easy to use that kind of features. So it's like you are not leaving your data anywhere else. It will be still with your databases, but still you can use that AI features integrating to your applications. Now, enterprises get most value by combining semantic search with value-based business data searches. So this is an example. Like you have a business database, you will have a lot of information that is private. That can be customer data, or it can be industry-related data, all sort of data that resides in your business database. In general, if you want to use a vector capability, you need to move this data to a vector database. There are vector databases that are used only for the vector search functionalities. So in order to do that vector functionality in your application, one of the solutions is continuously send the business data to a vector database. For example, if you are having a support incident database where you have all the incidents that are reported for a support application, you have to send that incident data to the vector database. Then you also need to send the product data, because you need to combine the product data and the customer data when you are doing a search for a particular information for use in the vector search. So it makes it to send a lot of data, because the search questions coming maybe that may need information about both the product and the customer data. So ultimately you will end up sending all your business data into a dedicated vector database. So it can get a lot of data staleness. It can add the complexity because you are moving a lot of data. It can compromise the security because you are sending the data out of your database. So also the enterprise databases, they will have a very large number of data, and it needs to have more sophisticated query capabilities. It also needs fault tolerance, security, etc. So these features are built on top of the databases that are used for the business purposes that may not be available in a normal vector database. So the vector approach that Oracle provides is like it's adding the vector search to your business database itself. So it can combine the value-based search that normally we does along with the semantic search. So it gives so many advantages. So how does this is happening? It is using a new vector data type that is storing the vector, and it using a new SQL syntax and functions to search the vector with the business. And it's also approximate search indexes introduced for high performance and quality. So with this one, there is no need to move or synchronize the data, or it's no need to move the multiple products, etc. Everything will remain in the business database itself, and we bring the the vector search capability to that database. Okay, these are some of the use case scenarios where the enterprise applications will use the vector search. So, for example, if you want to find a similar support tickets, if you have the application that is using for the support, uh, you can use the vector search in that one to find the similar previous support tickets that is filed already. Or if you want to look for the biometric pattern recognition, you can use the same technology. The same case with the similar products, or even finding defect manufacturing anomalies or product recommendations and natural language catalog search, etc. are some of the use case scenarios where the enterprise uses. Now, how this AI vector search and generative AI is combined together in an Oracle database. So, with the power of generative AI, vector search allows you to interact with the business data using the natural language. So we'll take one example where a normal LLM is being used to answer the question. So this is a typical case where a user can interact with the LLM and get responses. So this, in this case, right, like if you are using a chatbot or something, so in case if you have using that natural language questions to send to the LLM, what does it doing is it will generate the output using its own general knowledge. Okay, so here if you can see this document, it's the question being asked here is, why does my laptop keep rebooting? So this is an input from the user. The question is sent to the LLM, and the generative AI uses the user's question plus its general knowledge to generate the answer. So depending on your application, it probably give you a text response, and it is sent to the user, indicating, okay, because it is bad, maybe buy a new one. So that kind of response you will get when you use the LLM and the generative AI. So why the LLM is giving such a response? Because it can only give the response based on its general knowledge. That may not be so accurate in this particular case. Now, using LLM to answer your question may not be enough in all the cases, because large language models are trained on a broad range of data from the internet. But they are frozen on the past snapshot of the internet with no access to private enterprise data. So that whatever information it has, it is like a snapshot. So it will not change over the period. And also the same thing happens because LLM can be hallucinative, because it can give some inaccurate responses. So LLM by themselves therefore often provide poor quality responses to support questions. It's not the case with all type of applications, but the applications it needs the real-time data. It's going to give the response based on their knowledge. It may not be enough, but in some other applications that is enough, because it can have the uh, real-time data. So now how do we make a change to this this application, right? So AI vector search that can improve the generative AI by augmenting prompts with the private database content. So this helps to produce better answers to the user questions. And it's also avoid having to train the LLM on sensitive enterprise data. So basically, we wanted to give access to the private database when a query is coming. But at the same time, we don't need to train the LLM on the sensitive enterprise data. That means we still need to use the capabilities of LLM, but you cannot give your data to the LLM to train it with your enterprise data, because that data, it probably has to remain in your own enterprise world. You cannot give that because of so many restrictions. Now, how do we achieve this? This is being achieved through the retrieval augmented generation, or RAG. So RAG is combined with the AI vector search to achieve this goal. How do we do that? Okay, so the same example, if we take and if we improve this using the RAG and the AI vector search, it will be something like this. Okay, so a user natural language question is encoded as a vector and sent to the AI vector search. So instead of directly giving that to the LLM, the question is being encoded into a vector, and it is passed to the vector search database itself. So this vector search database will have your private data and the incidents that match the user question. So when I say incidents, this application, the application which is giving you response, right? Like, so your question was, why does my laptop keep rebooting? So consider this an application for a laptop related assistance providing company. So they may have a lot of similar incidents occurred in the past, or similar issues being reported by different users. All those information, like all those related incidents are like the reporting issues. So each time when customer is reporting an issue, that will be stored in their database. That is not available outside or it's not available to the public, because that information is specific to a particular company. So they will be using their own system and keeping track of all these incidents. So that information will be available with their database. Now we have included AI vector search capability to that database. So when the application is handling the user question, what happens is the AI vector search can go into the previously reported incidents. So it can access that data. Also, it can access the product and customer data, meaning like what was the for example, if this is a laptop, what type of laptop it was reported the same issue earlier, or what customer faced this issue earlier. So that kind of information relevant for the product and the customer. That will be available in the AI vector search database itself. That is the same your enterprise old database. But the but the uh, but the key thing is now you can use that information, incident reports and the product information from your own database to process the question from the user. So when we are giving that user question, that initial user question, it is now augmented with the relevant content. So it's not a generic question anymore. Now we have the background, we have added the relevant data that is helpful for the LLM to process this question. Now, look, if you look at the response from the LLM, now the LLM using that question and it's also using the content and the general knowledge to provide a better informed answer. If you see the answer, the LLM's response is the issue is with the firmware controlling the fan, apply OS update 42 while plugging and in a cool air conditioned environment to prevent overheating. So this is some response to your initial question. But this response is much improved because it's using the AI vector search and the additional context that is available in your database. So instead of giving a generic answer, if the customer is getting a specific response to their query, they will be more happy. So in order to achieve that one, enterprise can incorporate their AI vector search feature into the applications. So the answers or the responses can be much improved using the AI vector search. Now we are going more into the AI vector search to understand what is there in the AI vector. So these are the 5 key features of AI vector search that we will be discussing today. First one is how do we generate the vector embedding from the unstructured data? So as we saw, we need to have the vector generated in order to use that in our application. So we have a couple of options, both internal and external, to generate the vector embedding from the unstructured data. Now, after it's generated, it has to store into your database along with the other data. So for that one, we'll be using a new vector type that is added to the existing data type models in the Oracle database. Then build an approximate vector index or a vector column. So a vector index is the feature that makes this vector search faster. And also we need to provide new capabilities to perform the AI vector search using the SQL format itself. And finally, this needs to be integrated with the mission critical enterprise capabilities of Oracle and open source generative AI ecosystem. Meaning that it has to be compatible with the current capabilities of the database and the AI. So we'll go deep into each of this one. The first one is generate vector. How do we generate the vector? So vector embedding generation, you can do it in 3 ways. Oracle provide different options. How do you want to handle the generation of the vector itself? First one is use pre-created embeddings. So this means you can have your own vectors, that is you generated some time back, or you generated using any other third-party tool, and you can load that vector directly from the external files into the database, or it can be even mapped as an external table. In that way, you don't need to load even. You still can keep the data in your file as and when it's needed. These external tables will be fetching that data. So this way, you can bring your own data that is embedded and in the vector format. So this is useful when you already have some applications or your product that is already using the vector. Then you don't need to convert it again, but instead you can use that itself. Now, second way is use an external embedding service. So in this case, you have some data. For example, you have a list. You have the list of images that is present in your database, but you want to convert that to a vector. So in order to do that, you can use any external embedding service that is available now. So that embedding services can be called through this UTL2 embedding or the UTL2 embedding PLSQL function that is provided in the DBMS vector package. So it's like we are giving some options that you can use these options and use any third-party tool to generate the vector. Or even you can use the database resident embedding model. So in this case, this is the most secure way. So you already have your data, meaning like if your current application, for example, if it is using a search using the precision search, that means the value search, and if you want to convert that to an application where it can be used as a approximate search, like the vector search, in that case you need to convert your data, but that data is already present in your database. So you can use this vector embedding function that is available right now in 23 AI. You don't need to move the data outside your database. You simply use this function and create a vector data type to store that one. So in that way, the vector embedding generation is made simpler and more secure. So you can use any of these alternative options to generate the embedding vector. Now, you need to store the vector. Yeah, as we saw, like we have a vector data type to store and process the vector. So just like you had different data types earlier in the database, like for example, integer, varchar, character, like the lob data types, you can have a different data type that is called vector. This will be same as your any other data type, and it can have an optional dimension. When you are creating the vector, you can specify, okay, you are going to use these many dimensions. Remember, we see that each of the features in the house in that example, right? in each of the features that is represented as a vector dimension. So here you can have as many as dimensions you need to mention. I don't. I mean it. Uh, it can have thousands of dimensions. So there is an optional dimension format also you can mention. How do you want to store? What kind of storing format you need to use? It can be like float, 32, 64, integer, or binary. That kind of information you can provide. So this made even simple here because if you don't want to give these options, you can simply mention, okay, I need a column that is for the vector using the vector data type. The only thing you need to mention is the vector name and use the keyword vector. So it will create a table here using the vector I. So in this example, create a table support incidents. It will have the columns ID, incident text, and the incident vector. Just these three columns will be created using this query. Now, if you want to insert into this table, it's again the same SQL format. There is no difference. So you can give the values of all other columns, and also you can give this vector using this toVector function. The same way, if you want to see the vector, you can select from vector, incident vector from support incident, meaning like you can use the from vector function, use it in the table. Now, so this native vector support is also available in Python, Node.js, JDBC, or CA. All these drivers can use this vector data type using the APIs. Now we need to see like how the index vector is being used in the vector search. So this is a new vector index that provides 100 times faster and highly accurate similarity searches. So this is the key technology in the AI vector search in the Oracle database. So you can have different types of vector indexes added to your AI vector column. First one is neighbor graph index. Graph-based index where the vertices represent the vector and the edges between the vertices represent the similarity. So here we are not going into the details, but this is like a different types of vector, like the vectors you have earlier in your database. Similar to that, we have a totally new vector introduced to index the vector. So in this is, if you see this neighbor graph index, this is only an in-memory index. So that means it will be residing only in the memory. So it will be highly efficient for both accuracy and the speed. So the responses will be much faster. And the another type is neighbor partition index. So this partition based index with vector clustered into table partitions based on the similarity. So this is useful when you have your vector is in the range of millions or billions. So if you have a data that is too big, then you can scale out the index for unlimited data size. So in this case, what you are doing is you are putting the vectors into different partitions. So this gives you a more option, like you can scale out the index for any number of data. Now moving forward, how do we do the search of the vector? So here, if you look at the vector search, so the key feature you can use using the vector is the finding the distance between two vectors. Remember, we have similar vectors that will be placed closely, or if the similarity is more, then the distance between these two vectors will be known. So the vector search is using the same technique where you can have a SQL function to compute the distance between vectors to find out the similarity. So here you use this function, that is vector distance, and pass your vector and the input vector. Also optionally you can provide the distance matrix. How do you want to use that function? So different embedded models can use different distance metrics, but the same concept will be applicable for all of that models. The distance between two vectors is smaller for entities that are more similar. So the distance functions, there are different distance functions. The cosine is the default one. The other functions supported is Euclidean squared, Hamilton dot, etc. So in either case, always this will be the key feature in the vector search. Now, for example, if you want to search identifying the 10 top matching support incidents, you can do this search using this function. So it will be select whatever columns you need from the table, order by vector distance. You give the vector column and the input as binary variable, like what is the input vector. So you have a search vector. So that means if your application wants to find the similar incidents from your existing database, then you can use this query. So if you take the example of the laptop application, you have the all the previous incidents of a laptop failure reported in your application. So you can use your new scenario, that is the current vector. The incident that is reported will be converted to vector. Then you will pass that as the input for the query. So here you will be using vector distance function and find out the closed matching incidents. So it will fetch only the first 10 rows. If you give the clause that is fetch first 10 rows only. Now, so the vector search can combine the value based and the semantic search. So what does it mean is, the traditional database, it will be always using the exact value or the precision based search for their queries. But now, if you want to add that along with the semantic search, it's made so simple. So it means in this case, you want to find out the top 10 matching support incidents that were filed within last 7 days. So you wanted to see only those incidents that are filed or reported in last 7 days. So this is done easily using this query, where you can use the select query, the same select query, but you can enhance it with your where condition. So it means you can use the select from the table. You can use the where conditional. This is a traditional where condition, value-based where condition with the incident date greater than 6 date minus 7. That will give you the last 7 days of data ordered by the vector distance. That means again it's going to the vector and finding out 10 rows, because it's giving we are asking to give or fetch the first 10 rows. So value-based attribute filters can combine seamlessly with the vector search in SQL. Even though these queries looks simple, behind the scenes to implement these queries, it's much complex, because here you wanted to combine both different types of search, right? Like the the, the value-based search, which is normally we use, has to go with the semantic search. So the output, right, or the implementation of these queries are like as a DBA or a developer, if you want to use this query, for you the syntax is very simple, because it's almost the same as you used to write the query earlier. The only difference is order by clause in the query. But in reality, in the backend, they have done so many changes to make it simple for the interface. So many optimizer features are being included behind the scene, so that it can decide whether, for example, like in this case, like whether they want to go with the filtering the incident data first, or they want to do the distance function first, etc. So, but either case, the interface or the functionality provided such a way that the developer will be able to use it very easily. Now, the vector search semantic search can be even enhanced using the joins. So, if you are familiar with the SQLs, how the SQLs are being written in the real cases, right? Like you will have different tables. You need to combine different tables. You will have a complex query that is including the joins, etc. For example, if you find the top 10 matching support incidents for a laptop reported by customer in the Redwood shores. So this means it has to join more conditions, or it has to join with the different tables. So the normal query will be adding the where clause where you have the conditions from different tables. So instead of looking into the first table what we were created, that support incidents table, you need to join with your product. Maybe that product table will be there, and also you need to find the customers table that is having a connection with the product and the customer. And the reason is your application may be using different products. One of it may be desktop, it may be laptop. So you are asking only the incident that is part of the laptop. And also you wanted to find out what are the customers who has reported this issue from a particular region. So you have the product data and you have the customer data. Now you want to combine these with your incident. That is, the incident is the incident support incidents table is the one which is having the information about all the incidents that is reported to this application. So then you will do the combination of or join of these support incident with the product and the customer data. Now, this is again added to the vector distance function, where you can pass the vector as the input and fetch the 10 rows only. So as a result, right, what you are doing is you are combining the customer and the product data and the AI search in a simple SQL sentence. Again, this queries may look simple, but the yeah. So again, the queries may be simple, but it is adding the capabilities of both the AI search and the traditional database, like the RDBMS capabilities. So normally your data will be normalized. That is why you do have different tables. So any developer who wants to use this vector search, they can simply incorporate the vector search functionality just by adding the vector distance function. Now, how do we integrate with your existing features to AI vector search? So again, I was telling in the starting of the session that okay, this you need to think as an enterprise application model, because we are adding a new feature or the functionality to the existing model. Now, if we are not able to include all the existing features to this particular new capability, you will be doing a lot of rework, both for your application and for your database. But Oracle has integrated all these existing features into the new functionality that is provided. So that makes this product even powerful, because it comes with the existing capabilities added to the new function. So integrate with the mission critical enterprise capabilities. Now, this is only a few examples I'm going to give here. So if you take the case of transactions, so suppose you have you are using any of this index type, like maybe the neighbor partition vector index or the neighbor graph vector index. So this has to maintain the traditional transactional consistency with the DML activity. So it has to basically the RDBMS is based on the transactional consistency. So it cannot violate that. So when you have a new vector inserted, you still need to keep that consistency with any of the DML activity, like any data manipulation that you are doing. It has to comply with that. So vector search functionality is ensured that it will go along with the transactions. And scale out with the real application cluster. So real application cluster or rack, this is something we introduced in the database. So you can have different nodes or different instances running for a single database. So in this case, we are dividing the work across the different compute nodes in the rack cluster. So when you add the AI vector search, that also has to correspondingly scales vector processing across the compute nodes in a rack cluster. You can have different nodes, like in any rack cluster environment. Instead of having one instance, you may be using 3 or 10 instances. So this has to go transparently, because you cannot have only one instance using the AI vector search instead of means you cannot have only one instance alone, but you may have different instances. All of them are going to use the same AI vector transparently using the vector search. So this comes with the full data consistency, because it has to keep that RDBMS model. Whatever is we have built on top of that model only. Now, those two are just examples, but we do have so many features that already implemented in the database, right? Like you can have the partitioning. Sharding is something like you can keep your data in different geographical regions. Security is another aspect. Transactions we already saw. So the parallel execution of this queries, analytic features, and the rack capabilities, and also the Exadata. So the Exadata is something like you can have the complete stack of the application. Like when you are using the Exadata databases, you will get the hardware and the network software, database software, everything included in the Exadata. So all these features are existing already in the RDBMS world that is provided by Oracle. So now when we come up with a new search technology, we wanted to integrate all these functionalities into the vector search also. So it's actually adding a lot of work behind the scene, but for a application user, it is becoming transparent. For example, if you are used to have a different, if you are used to have a parallel execution query in your application, when you are bringing the vector search, you don't need to change anything. The vector search is also going to do the parallel execution. So that way, your application faces limited change, but you still get the capabilities that were existing earlier. Okay, so with that, I'll go into the towards the end of our presentation. That is the key takeaways, right? Just to recap, so Oracle database 23 AI introduced the AI vector search in the database, and vectors are the mathematical representation of text, image, or other data. Perform the sophisticated information retrieval by combined semantic search with the value-based search on your own business data. That is why we are using the AI vector search. So it combines the power of semantic search along with the traditional value-based search. So we do have new vector data type. We have a new SQL syntax to query, and we have approximate search index, which is the key functionality that provides the faster responses for a vector search. Now, these are some of the references or the data you can refer to get more information about the AI vector search in Oracle database. So these all links point to the Oracle site, where you can get a lot of information. So along with that, there are products provided by Oracle that can be used without any cost. Like you can use these products if you go to these labs or this hub information page, you will see a lot of tools that can be used. And when the Oracle released the new database, that is Oracle 23 AI, that is released as a free, so you can go and download like with a zero cost. So you can start. I mean, if you want to play this new features, it's readily available. And this live lab is very good place where you can do your own projects and all, like not just for the AI search, but it is giving so many interfaces that can be used to try out any of the Oracle database features. So yeah, with this one, I'll conclude. Thank you for your time. And if you have any questions, we can discuss.
There is any question from participant side? Okay, hope there is no questionnaire session. So today's conclusion, I request Associate Professor of PhysAt, Dr. Hema Krishnan, for the vote of thanks. Miss, please.
I'm audible. Am I audible?
Yes, ma'am.
Okay. Good evening, everyone. It's my privilege to extend a vote of thanks as we conclude today's session of 6-day faculty development program on strategic approaches and emerging trends in data science. First and foremost, I would like to express my sincere gratitude to our esteemed resource person, Mr. Anand George, Principal Technical Engineer, Oracle America, USA. Thank you so much, sir. We are grateful for the time and the effort you have invested in preparing and delivering such a remarkable presentation. Your session was truly inspiring and provided us an awareness of Oracle database and also a deep knowledge of AI and how to apply AI for doing vector search in Oracle database. On behalf of PhysAt, I would like to extend my heartfelt appreciation to you, sir, our esteemed resource person, Anand, sir, Principal Technical Engineer, Oracle America. Thank you so much, sir. I would also take the opportunity to express my gratitude to all the participants who have actively engaged, asking questions, and also made the session more interactive. Once again, thank you, Anand sir, and all participants.
Thank you.
Yes, sir. Regarding tomorrow's sessions, there will be 3 sessions tomorrow. First session from 2 p.m. to 3:30 p.m. The topic is Python for data science and research, and Expert name, Dr. Shainu PG, Professor, Department of Computer Applications, Vellore Institute of Technology, Chennai. Second session will be from 3:30 p.m. to 5 p.m. on topic Generative AI by Mr. Rajiv M.A., Enterprise Architect, TCS Cochin. And the last topic is Generative AI for Purpose LED Innovations by Mr. Robin Tommy, Innovation Head, TCS Trivandrum. That is from 6:30 p.m. to 7:30 p.m. And we have a valedictory function from 7:30 p.m. to 8 p.m. followed by an online test and feedback. Thank you so much once again and see you all tomorrow. Thank you.
Thank you, ma'am.